In this lecture, we'll continue with our treatment of differentiation rules. First rule we'll cover today, product rule. And so anytime you're taking the derivative of a product of two functions, this will be the rule to follow. So if f and g are both differentiable at x, then so is their product. And we have the rule listed here. So the derivative of the product of f and g, we have the derivative of g times f plus the derivative of f times g. I always remember this just saying the first times the derivative of the second plus the second times the derivative of the first. Now, given the types of functions that we've seen so far, which essentially up to this point has been polynomials, we could compute the derivative of this m of x simply by foiling this out and then using our rules, power rule and rules for linear combinations. However, we can try this product rule, and this will work just fine. So our derivative, m prime of x, will be the first, x squared plus 1, times the derivative of the second, and for the second term in parentheses, we go term by term, 3x squared minus 1 plus 0. Then we go plus the second times the derivative of the first. So we have x cubed minus x plus 4, and the derivative of the first, 2x plus 0. You get the same answer if you FOILed this out and did the derivative using tools that we already knew before today. So this is the idea of product rule. As well, before we derive it actually, let's also write it another way. So another way we often write it using this differential notation. If we have the derivative of the product of functions u and v, so here think of it as u is our f of x, v is our g of x. Then we write this as the first times the derivative of the second, dv dx, plus the second times the derivative of the first, du dx. This is the same rule as written here, just with different notation. How does this rule work? Where does it come from? Let's derive our product rule. And remember that we always go back to the definition of derivative here. So we want the derivative with respect to x of the product of f of x and g of x. And our derivative definition tells us this is the limit as h goes to 0. Evaluate this piece here at x plus h. So first we have f of x plus h times g of x plus h minus this expression evaluated just at x. So f of x times g of x all over h. And we now simplify this. And the first step in doing this is kind of a creative step of adding and subtracting the same factor to the expression. So we're still going to have this f of x plus h times g of x plus h. But we then add and subtract. So we subtract f of x times g of x plus h, and then we add it back. F of x times g of x plus h. And then we still have the minus f of x times g of x term. So we haven't changed anything. But we now can group things. So we can group things in the following way. So we want to take this g of x plus h term that's paired with the f of x plus h term as well as the f of x term. So we will now pair these two. And similarly, we will pair these two. So this is the limit, as h goes to 0, of 1 over h. And we'll now use the sum law to break the limit of the sum of these two pairs into the sum of the limits. And notice that we can also do some factoring. Maybe we'll do factoring in a second step. Here we have f of x plus h well, maybe we can see the factoring now. See it in this first pair here. We have a g of x plus h common to both terms. So we can factor that. So we'll factor it out here on the right. So we have this whole limit expression. And then we have a similar limit expression for this here, except now we can factor out an f of x. So we have f of x times g of x plus h minus g of x. And we have still 1 over h. Don't forget that. So all that was done here, 2 steps. The limit of the sum of these two orange paired terms was broken to the sum of the limits of those terms, and we just did a factoring step in each case. Now, this f of x term here has no h appearing in it. So as far as this limit is concerned, f of x will behave like a constant, which means it can be factored outside of that term. Here, we're going to use our limit law, our product law, and so the way we will pair things now is the h is going to stick with the differences of the f's. So the second term is the easier term. But again, here in the first term, we have f of x plus h minus f of x all over h times the limit as h goes to 0 of g of x plus h. Again, that's using what we were calling our product law for taking limits. And again, it works because both of these limits will exist on their own. And again, on this side here, we've taken that f of x outside the limit. And if you now note these limits, this limit here is the definition of g prime of x, and this limit here is the definition of f prime of x. And because g of x is differentiable, therefore it's continuous, we actually can bring this limit inside, and this becomes g of x. So note what you have. F prime of x times g of x plus f of x times g prime of x. So we have exactly our product rule. Again, it's important to understand where these come from because you want to realize that anytime you're using differentiation rules of any kind, you are actually using this definition of derivative. Again, it's just like thinking of if you're driving a car, you're using the internal combustion engine. We want to be more than just drivers of the car. We want to be mechanics. We want to be able to drive the car and understand the car, how it works. So this is the engine that's driving all the differentiation rules that we're learning. Okay, so that's our product rule. The next rule is a rule that we actually will use more like a stepping stone. This is a rule that you're not going to really work with very much directly. Our reciprocal rule gives us a method for finding the derivative of the reciprocal of a function, as long as the function is not 0 at a given x, so that we can't have a division by 0. Essentially, we're developing this rule so that we can use it to derive the quotient rule. Now, for this rule, again, we start out as usual with the definition of derivative. So the derivative with respect to x of the reciprocal of f of x is, using the definition of derivative, the limit as h goes to 0 of, dividing by h, so we'll write it as 1 over h. We first evaluate this expression at x plus h, so 1 over f of x plus h. Then we subtract just a function evaluated at x. So remember, think of this. This is the numerator. This is the expression evaluated at x plus h minus the expression evaluated at x, all divided by h. So that's our standard definition of derivative. Now, our next step will be to get a common denominator here. And so we need to multiply each term by the correct form of 1 to get our common denominator. So for the first term, we multiply by f of x over f of x. And then for the second term, we'll multiply by f of x plus h over f of x plus h. Which now gives us, and don't forget the 1 over h. So this now gives us the limit as h goes to 0 of f of x minus f of x plus h over the product of f of x times f of x plus h. All multiplied by 1 over h. We now use our limit rules, well, our product limit rule, where we isolate these terms from these terms. So what we were calling our product law. This is the limit as h goes to 0. The terms circled in blue. F of x minus f of x plus h all over h times the limit as h goes to 0 of 1 over f of x times f of x plus h. Note, this is the definition of minus f prime of x. this term here, because since f is differentiable, and actually this is a theorem that we haven't proved yet, but we will in a few minutes. Because f is differentiable, it's also continuous, which means we can directly evaluate this. We can use our quotient law and our product law for calculation of limits, and then we can actually bring the limit inside of here, which results in this limit being 1 over f of x squared. So this becomes negative f prime of x over f of x squared, which is the rule we were trying to prove. So this gives us a method, again, for calculating the derivative of a reciprocal of a function. So for example, consider this function. And let's just write it down. Our reciprocal rule, the derivative of 1 over f of x with respect to x, is the negative of the derivative f prime of x over f of x squared. And when you use this limit, this reciprocal rule, you want to identify this denominator as your f of x. So our derivative, g prime of x, applying our reciprocal rule with this denominator playing the role of f, will have the negative of its derivative, so calculate the derivative term by term, 4x cubed plus 2x plus 0, over f of x, that denominator here, squared. So over quantity x to the fourth plus x squared plus 1, all squared. And so this is how we can use our reciprocal rule to get derivatives. And again, this is not a rule that we are going to use very much. Really, it's a rule that we're using as a vehicle for the next theorem. So the next rule is a really convenient rule, and it's the power rule for negative integer exponents. If n is a negative integer, then a derivative with respect to x of x to the n is nx to the n minus 1. Same power rule that we had seen before. The proof of this uses reciprocal rule. So if n is a negative integer, we can say n is less than 0. And let's just let m be its negative. So that'll be a positive value. This means x to the n, so our function of concern, can be written, just using the rules for exponents, 1 over x to the negative n, but that's 1 over x to the m, using this new convention that we have. And m, of course, by construction, was positive. And this, x to the m, we will now call f of x, and directly use the reciprocal rule. So, f of x is x to the n. So this means the derivative of our x to the n is the derivative of 1 over x to the m. And our reciprocal rule said that's minus f prime of x over f of x squared. X to the m is positive, so this is like x to the fifth or x to the eighth. We can take its derivative just using power rule. Power rule for positive integer exponents, which we already know, And so we know, so don't forget we have this minus sign. So minus, and then we have mx to the m minus 1, again by power rule. And in the denominator, we have x to the m squared. And all that remains here is just to clean this up algebraically. So we have minus m x to the m minus 1 over x to the 2m. And remember your rules for exponents. We can now bring this x into the numerator, and we get an x to the minus 2m. But now these are the same base, so we can add the exponents. So this is minus m. We add the exponents. So we have m minus 2m, which is minus m, and x to the minus m, and that minus 1 is still there. Now recall that m is minus n. So if m is minus n, we can multiply both sides by minus 1 to get n is equal to minus m. So this minus m is n, and this minus m is n, which means this is n x to the n minus 1. So reciprocal rule is what got us there. And what's really nice about this, it's nice when you don't have to learn different rules for different cases. And you don't. If you have x squared or x to the minus 2, your power rule is the same. You bring the power out front, and then you reduce that power by 1. So we'll see some examples of this. But we also will make the point, and this is a rule that we won't prove, but what if r, your power of x, is rational? So this bold-faced math Q stands for the rational numbers. And remember, rational number just means it can be written as p over q, where p and q are integers. So the definition of rational means it can be written as the ratio of two integers. So if you have a rational exponent, the power rule is the same. You bring the exponent out front, and then you reduce the exponent by 1. This expands our toolkit dramatically for taking derivatives. So we can take a look at this case and get g prime of x. And it's always nice when you see these types of expressions, in my opinion, to get all of your x terms in the numerator and write with rational exponents. So square root of x is x to the 1/2. This term here, middle term, cube root of x, that's an x to the 1/3. But if we bring it into the numerator, it'll be x to the minus 1/3. And then we have minus, if we bring the x to the 7th up top, it's x to the minus 7. And we can now differentiate term by term. And again, we're using the same power rule. So for this first term, the 1/2 comes out front. And then we'll be very explicit to see how this works. And then you subtract 1 in the exponent, just like before. For the next term, the minus 1/3 comes out front. And then you subtract 1 in the exponent. For the next term, we have a minus 7 coming out front. And you subtract 1 in the exponent to get g prime of x. Now we simplify. 1/2 minus 1 is negative 1/2. Then we have minus 1/3. Negative 1/3 minus 1 is minus 4/3. Then we have a minus minus, so plus 7x minus 7 minus 1 is minus 8. If you want this first term, you could write as 1 over 2 root x. But of course, either way is fine. But the point is, you're using the same power rule for any exponent. We didn't say it for real exponents, but it actually holds in that case too. Just be careful with your calculations. It can be really easy to make mistakes when you do these derivatives of terms with rational exponents. Mistakes are very common. Our last rule for this lecture will be quotient rule. Quotient rule is for division of functions, but it's also the case that you don't really need it because you can actually always use product rule if you want. So if you find yourself not remembering quotient rule, you can just write it as the derivative of f of x times 1 over g of x and just work through it with product rule, and it will work out just fine. And in fact, you'll see in the proof that that's all it is it's just an application of product rule. So to set this up, we do exactly what we've written above here. We're going to look at that derivative of f of x times 1 over g of x. And we use our product rule. So remember, product rule says first times the derivative of the second plus the second times the derivative of the first. So we have first, and to get the derivative of the second, we use our reciprocal rule. Maybe we should be more explicit. So derivative with respect to x of 1 over g of x plus the second 1 over g of x times the derivative of the first, right? And here is our reciprocal rule. So this term will be minus g prime of x over g of x squared so we get f of x times g prime of x. We have a minus sign over g of x squared plus 1 over g of x times f prime of x. And what we notice here is that we have an extra g of x term in the denominator here. So we multiply this term on the right by g of x over g of x. And that gives us exactly what we want. We now have this first term is minus f of x times g prime of x. Then we have plus f prime of x times g of x all over g of x squared. And notice that this is exactly what we have up here. I tend to use a similar kind of way of remembering this to the product rule, where you say, read this denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. But again, it is just, to get it, you just need product rule. So if you ever find yourself forgetting this, just revert back to product rule. Rewrite the quotient as the multiplication of function and its reciprocal. As an example, let's directly apply this quotient rule. So to get f prime of t, again, come back, g is the denominator. So denominator times the derivative of the numerator. So the denominator is 2t to the fourth plus t cubed plus 4. The derivative of the numerator is 2t. And we have minus the numerator times the derivative of the denominator, 8t cubed plus 3t squared. Derivative of 4 is, of course, 0, all over the denominator squared. So there's our application of the quotient rule. The last topic that we'll look at here, we already have referenced. That's okay. This is a pretty natural idea, is that if a function is differentiable, then it's also continuous. So if a function f is differentiable around a point A, in an open interval containing A, then it's also continuous at A. And essentially the idea of continuity, remember that continuity was draw the graph without ever taking the pen off the paper, but I could have cusps or corners, maybe not that one, it's got to be a function, but you can have cusps or corners. So this is what continuity looks like, but you don't have differentiability at these types of points, which we'll get into in the next lecture. But the idea of differentiability is smooth. It has, in addition to the property that to draw the differentiable function, I put the pencil on the paper and don't take it off, I also have to draw it in a smooth way. You can't have these types of corners or cusps. So there are more restrictions on a differentiable function than on a continuous function. And it's true that if your function is differentiable, it's also continuous. And this is a quick proof. Remember that the idea of continuity is that not only does the continuity of a function f at A, you need the limit as x goes to A of f of x to exist, and it also has to equal f of A. So if we can show this using the definition of derivative, then we can conclude that if you're differentiable, if your f is differentiable at x equals A, it is also continuous at x equals A. So the way that we'll do this is, let's look at this at the difference of these two. So we're going to look at the limit as x goes to A of f of x minus f of A. And of course, we can, f of A does not involve x at all. And if we want, we can go ahead and bring it inside of the limit, because as far as x is concerned, it's just a constant. And this allows us to then multiply by a convenient form of 1 and then group things accordingly. So we group things by writing this as a limit as x approaches A of f of x minus f of A over x minus A. So we took this x minus A that we introduced in the denominator and paired it with this f of x minus f of A, and we left the other x minus A out front. We can then use our limit laws to argue our product law, that this is the limit as x goes to A of f of x minus f of A over x minus A times the limit as x goes to A of x minus A. So again, using our product law for limits. And this expression here is another way of writing f prime of x. And you can think of that by, if you look at the picture, think of this x minus a as your h. So you have your h in the denominator, and then you're letting x approach a, which is just like letting h go to 0. So this is very similar. It's just another way of writing the derivative. You would have f of x. Here's our f of a. Here's our f of x. And so if you look at the secant line, its slope is, of course, rise over run. Which is the rise is f of x minus f of a. All over the run, which is x minus a. Which you see is exactly what we have here. So this is another way of expressing the difference quotient, where you have the slope of the secant line. And then when you let h go to 0, or equivalently in this case, x go to a, the secant line becomes the tangent line, and this becomes f prime of x. So point is that this exists because f is differentiable at a. Sorry, this is actually, I made one slight mistake there. This is actually f prime of a. And this limit here, yeah, so this is at a, this f prime. So that exists because f is differentiable at a. That's some finite number. But this, by direct evaluation, is 0. Which means this whole expression is 0. Which is what we wanted to show. With this expression being 0, that means we got what we wanted. So that concludes the proof. And this is the formal proof that shows us that if a function is differentiable at a point, it also has to be continuous at a point, at that same point. The other way around is not true. Continuous functions can have these corners and cusps. At those places, you don't have a tangent line existing. And so you have the function not being differentiable.